Welcome to this coding problem walkthrough. Today, we'll be diving into the problem longest harmonious subsequence, where we'll explore an efficient way to solve it. Let's get started. In this problem, we are tasked with finding the longest harmonious subsequence in an integer array. A harmonious subsequence is defined as a subsequence where the difference between the maximum value and the minimum value is exactly 1. The goal is to determine the length of the longest such subsequence in the given array. The input is an integer array, where the length can range from 1 to 20,000, and the values can range from -1 billion to +1 billion. The output will be a single integer that represents the length of the longest harmonious subsequence. If no harmonious subsequence exists, the output should be 0. Let's explore some examples to understand this definition and the problem more clearly. In the first example, we have the input array nums equals 1, 3, 2, 2, 5, 2, 3, 7. The output is 5 because the longest harmonious subsequence is 3, 2, 2, 2, 3. Here, the difference between the maximum value, which is 3, and the minimum value, which is 2, is exactly 1, satisfying the condition for a harmonious subsequence. Moving to the second example, we have the input array nums equals 1, 2, 3, 4. The output is 2 because the longest harmonious subsequences are 1, 2, 2, 3, or 3, 4. Each of these subsequences has a length of 2, and the difference between the maximum and minimum values in each case is 1. Now, consider the third example where the input array is nums equals 1, 1, 1, 1. The output here is 0 because no harmonious subsequence exists. All the elements in the array are the same, so the difference between the maximum and minimum values is 0, which does not satisfy the condition for a harmonious subsequence. It's important to note that the constraints are designed to test the efficiency of your solution. The array length can go up to 20,000, and the range of values is very large, spanning from -1 billion to +1 billion. This means your solution needs to be optimized to handle these scenarios effectively. Finally, let's discuss some edge cases that you need to consider for this problem. First, if the array contains only a single element, such as 1, the output will be 0 because a single element cannot form a subsequence with a difference of 1. Second, if all elements in the array are identical, like 5, 5, 5, the output will also be 0, since no harmonious subsequence can exist. Third, your solution must handle arrays with a very large range of values efficiently, ensuring that it works even when the values span from -1 billion to +1 billion. Lastly, for cases where the array length reaches its maximum constraint of 20,000, your implementation should be optimized to process the input within a reasonable time. By addressing these edge cases, you'll ensure your solution is robust and performs well across all scenarios. To solve the longest harmonious subsequence problem, the brute force approach is a straightforward starting point. The intuition behind this method is to generate all possible subsequences of the given array, then check if each subsequence qualifies as harmonious. A harmonious subsequence is one where the difference between the maximum and minimum values is exactly 1. In terms of implementation, we iterate through all subsets of the array, calculate the maximum and minimum values for each subset, and verify whether the difference meets the condition. While doing this, we track the length of the longest harmonious subsequence encountered. However, generating all subsets of an array has a time complexity of O(2 to the power of n, and for each subset, calculating max and min adds an O(n) factor, resulting in a total complexity of O(n*2 to the power of n. This is computationally expensive and impractical for large arrays. Additionally, the space complexity is O(1) for extra space, but this ignores the overhead of subset generation. The primary limitation of this approach is its exponential growth, making it infeasible for real-world use cases with larger input sizes. Now, an optimized approach using a hash map offers a much more efficient solution. The key observation here is that a harmonious subsequence must contain elements with values differing by exactly 1. Instead of generating all possible subsets, we leverage a frequency map to count how many times each number occurs in the array. With this map, we can focus directly on pairs of consecutive numbers, such as a key and its neighbor, key plus 1. For implementation, we first build the frequency map using a dictionary. Then, for each unique number in the map, we check if its consecutive neighbor exists. If it does, we calculate the total frequency of the pair by summing the counts of the current number and its neighbor. The maximum length of such pairs is updated as we go. This method is highly efficient, with a time complexity of O(n), as we only traverse the array once to create the frequency map and then iterate through the unique keys. The space complexity is also O(n), as we store the frequency map. By avoiding the generation of subsets, this approach drastically reduces computational overhead and scales well for large arrays. The trade-off is that it requires additional storage for the hash map, but the efficiency gains far outweigh this cost. Finally, it's important to note that the sliding window technique, which is often used for contiguous subarray problems, does not apply here. Since this problem involves non-contiguous subsequences, a sliding window approach is not suitable. Among the methods considered, we chose the optimized approach using a frequency map because it strikes the perfect balance between time and space complexity. The key insight lies in recognizing that we only need to focus on pairs of values differing by 1, and these pairs can be efficiently identified using a hash map. Compared to the brute force method, this approach eliminates unnecessary computations by leveraging the problem's constraints. It directly calculates the longest harmonious subsequence in linear time, making it both clear and efficient. By focusing on the frequency of elements and their neighbors, we achieve a scalable solution that is well suited for large input sizes. In this problem, we are tasked with finding the length of the longest harmonious subsequence in an array. A harmonious subsequence is defined as a subsequence where the difference between the maximum and minimum values is exactly 1. Importantly, the array may contain duplicates, and we need to focus on finding an efficient solution since generating all possible subsequences would be computationally expensive. To achieve this, we'll use a frequency map. This approach allows us to avoid inefficiencies by directly leveraging the counts of numbers in the array. First, let's establish the key constraints. A harmonious subsequence must have a max-min difference of exactly 1, and since we're working with subsequences, the order of elements in the array doesn't matter. Our goal is to determine the length of such a subsequence, not to explicitly construct it. The frequency map is central to our strategy because it enables us to quickly check, for any number x, whether x plus 1 exists and, if so, compute the length of the subsequence formed by these two numbers. The length is simply the sum of their frequencies in the array. To implement this approach, we start by constructing a frequency map to count how many times each number appears in the array. This map will allow us to efficiently check whether x plus 1 exists for each number x and retrieve their frequencies in constant time. Then, we iterate through the unique keys in the frequency map. For each key x, we check if x plus 1 exists in the map. If it does, we calculate the total length of the harmonious subsequence formed by x, and x plus 1 is the sum of their frequencies, frequency, x, plus frequency, x plus 1. As we perform this calculation, we keep track of the maximum length encountered so far. Once all keys in the map have been processed, the maximum length we've tracked is the length of the longest harmonious subsequence. The frequency map is a critical optimization here because it allows us to focus only on pairs of adjacent numbers in the value space, rather than generating all possible subsequences. This drastically reduces complexity. While a brute force approach involving subsequences would have exponential time complexity, our optimized approach brings the complexity down to linear time for constructing the map and a linear pass through the unique keys, making it highly efficient. The overall time complexity of our approach is O(n plus k), where n is the size of the array and k is the number of unique values in the array. Since k is at most n, this simplifies to O(n). The space complexity is also O(n), as we store the frequency map. Let's also address some important edge cases. If the array is empty, there are no elements to form a harmonious subsequence, so the result should be 0. Similarly, if all elements in the array are the same, the difference between the maximum and minimum values is 0, which doesn't satisfy the problem's constraints, so the result should again be 0. If the array has only one element, it's impossible to form a harmonious pair, so the result is also 0. The frequency map is a robust data structure for this problem, as it efficiently counts occurrences of each number and allows constant time lookups for any x plus 1. To tie this all together, we can look at the Python implementation. It starts by building the frequency map using the counter class from Python's collections module. Then, it iterates through each unique number in the map, checks for the existence of x plus 1, and computes the length of the subsequence if both numbers are present. Finally, it returns the maximum length found during the process. Let's walk through an example to see how this works in practice. Consider the input array 1, 3, 2, 2, 5, 2, 3, 7. First, we construct the frequency map, which shows the count of each number 1, 1, 3, 2, 2, 3, 5, 1, 7, 1. Next, we iterate through each key in the map. For the number 1, we check if 1 plus 1 equals 2 exists. It does, so we calculate the length of the subsequence as 1 plus 3 equals 4. For 3, we check if 3 plus 1 equals 4 exists. It does not, so we skip it. For 2, we check if 2 plus 1 equals 3 exists. It does, so we calculate the length as 3 plus 2 equals 5. For 5, we check if 5 plus 1 equals 6 exists. It does not. Finally, for 7, we check if 7 plus 1 equals 8 exists. It does not. The maximum length encountered during this process is 5. This example highlights how the frequency map allows us to efficiently calculate the length of harmonious subsequences without unnecessary computations. The time complexity is linear, as we only process each number once, and the space complexity is also linear due to the frequency map. This makes the solution both elegant and highly efficient for large input arrays. This is the Python implementation of the solution to LeetCode problem number 594, longest harmonious subsequence. The problem asks us to find the length of the longest harmonious subsequence in an array, where a harmonious subsequence is defined as a subsequence where the difference between the maximum and minimum values is exactly 1. ###line-by-line explanation. 1. We begin by importing the counter class from the collections module. This will help us efficiently count the frequency of each number in the input array. 2. Inside the findLHS method, we create a frequency map of the input array nums using counter nums. This map tells us how many times each number appears in the array. 3. We initialize a variable max_length to 0. This will track the length of the longest harmonious subsequence we find. 4. Next, we iterate through each key in the frequency map. For each number, we check if number plus 1 exists in the frequency map. This is because a harmonious subsequence requires the difference between the maximum and minimum values to be exactly 1. 5. If number plus 1 exists, we calculate the length of the subsequence formed by combining all occurrences of number and number plus 1. This is done using frequency, number, plus frequency, number plus 1. 6. We then update max_length with the maximum of its current value and the length of the subsequence we just calculated. 7. After iterating through all the numbers in the frequency map, we return max_length, which holds the length of the longest harmonious subsequence. ### complexity analysis. Time complexity, the solution runs in O, n, where n is the length of the input array. This is because creating the frequency map and iterating through its keys are both linear operations. Space complexity, the space complexity is O, U, where U is the number of unique elements in the array. This is due to the storage required for the frequency map. This implementation is efficient and concise, making it well suited for solving the problem at scale. This is the Java implementation of the longest harmonious subsequence problem on LeetCode. The logic mirrors the provided Python solution. The Java implementation uses a hash map to create a frequency map of the input array, iterates through the keys, and checks for consecutive numbers. The maximum length of such harmonious subsequences is calculated and returned. Key differences include explicit type declarations, Java's map interface for the frequency map, and usage of math.max for updating the result. To solve this problem, we start by analyzing the given input array nums equals 1, 3, 2, 2, 5, 2, 3, 7. The first step involves creating a frequency map using the counter class. This map tells us how many times each number appears in the array. Here, the frequency map is frequency equals 1, 1, 3, 2, 2, 3, 5, 1, 7, 1. Next, we iterate through each number in this frequency map to calculate the length of any harmonious subsequences. We also initialize max_length equals 0 to keep track of the longest subsequence found so far. For number equals 1, we check if number plus 1, which is 2, exists in the frequency map. Since it does, the length of the harmonious subsequence formed by 1 and 2 is frequency 1 plus frequency 2 equals 1 plus 3 equals 4. We then update max_length to 4. Next, for number equals 3, we check if number plus 1, which is 4, exists in the map. It does not, so we skip this number and move on to the next one. Continuing with the iteration, we now examine number equals 2. Here, number plus 1 is 3, and since 3 exists in the frequency map, we calculate the length of the harmonious subsequence formed by 2 and 3 as frequency 2 plus frequency 3 equals 3 plus 2 equals 5. This length is greater than the current max_length of 4, so we update max_length to 5. For number equals 5, we check if number plus 1, which is 6, exists in the frequency map. It does not, so we skip this number. Similarly, for number equals 7, we check if number plus 1, which is 8, exists, but it also does not. Having completed the iteration, we find that the longest harmonious subsequence length is max_length equals 5. Now let's analyze another example with input nums equals 1, 2, 3, 4. The frequency map for this array is frequency equals 1, 1, 2, 1, 3, 1, for 1, which means each number appears exactly once. We initialize max_length equals 0 and iterate through the frequency map. For number equals 1, we check if number plus 1, which is 2, exists in frequency. Since it does, we calculate the length of this harmonious subsequence as frequency 1 plus frequency 2 equals 1 plus 1 equals 2. We then update max_length to 2. Next, for number equals 2, we check if number plus 1, which is 3, exists in the map. It does, so we calculate the length as frequency 2 plus frequency 3 equals 1 plus 1 equals 2, but max_length remains 2 because the new length is not greater than the current value. We continue iterating through the frequency map. For number equals 3, we check if number plus 1, which is 4, exists in frequency. It does, so we calculate the length of this harmonious subsequence as frequency 3 plus frequency 4 equals 1 plus 1 equals 2. The value of max_length stays at 2 as the calculated length matches the current maximum. Finally, for number equals 4, we check if number plus 1, which is 5, exists in the frequency map. It does not, so we move on. At the end of the iteration, the longest harmonious subsequence length for this example is max_length equals 2. In the final example, the input array is nums equals 1, 1, 1, 1. The frequency map here is frequency equals 1, 4, indicating that the number 1 occurs 4 times. We initialize max_length equals 0 and iterate through the frequency map. For number equals 1, we check if number plus 1, which is 2, exists in the map. It does not, so no harmonious subsequences can be formed. As a result, the longest harmonious subsequence length remains max_length equals 0 for this example. To analyze the time complexity of our solution, let's first look at the construction of the frequency map. Using the counter nums function, we traverse the entire input array once, counting the occurrences of each element. Since we're making a single pass through the array, this step takes n time, where n is the length of the array. Next, we iterate over the keys of the frequency map. Let's denote the number of unique elements in the array as k. In the worst case, where all elements are unique, k would equal n. Thus, iterating through the keys takes k, which simplifies to n. Additionally, for each unique number, we check if its consecutive number exists in the frequency map using the if number plus 1 infrequent condition. Thanks to Python's efficient hash table implementation, this lookup is an O1 operation on average. Since we perform this check for every key, the total contribution of these lookups is k, which again simplifies to n. Now, let's consider the final step of updating the maximum length. For each iteration, the max function is used to compute the maximum length of the harmonious subsequence. This is a constant time operation, O1, for each iteration. Over k iterations, this adds up to k, which is n in the worst case. By combining all these steps, frequency map construction, iteration through the keys, and updating the maximum length, the overall time complexity of the solution is O(n). Moving on to space complexity, the primary contributor is the storage of the frequency map. In the worst case, where all elements are unique, the frequency map will contain n entries, requiring O(n) space. Aside from this, the algorithm uses a few auxiliary variables, such as max_length and number, which take up constant space, O(1). Therefore, the overall space complexity is dominated by the frequency map, resulting in O(n) space usage. Let's compare the optimized solution to a brute force approach. A naive solution would involve iterating through every pair of elements in the array to check if their difference is exactly 1, and then summing their frequencies. This approach would require nested loops, resulting in O(n²) time complexity. However, it uses no additional data structures, so its space complexity would be O(1). In contrast, the optimized solution uses a frequency map to avoid redundant computations. By pre-computing the frequency of each element, we reduce the time complexity to O(n), while increasing the space complexity to O(n) due to the frequency map. This trade-off is highly favorable for larger inputs. When analyzing the best, average, and worst-case scenarios, we see that the time complexity always remains O(n). In the best case, where the input array has very few unique elements, the frequency map is small, and the algorithm finishes quickly with minimal overhead. In the average case, with a moderate number of unique elements, the time complexity is still O(n). Even in the worst case, where all elements are unique, the algorithm performs efficiently, processing each element exactly once. To solidify our understanding, let's mathematically prove the algorithm's big O complexity. The first step, constructing the frequency map, is an O(n) operation since it processes each element in the input array once. The second step, iterating over the unique keys of the frequency map, is O(k), where k is the number of unique elements. For each key, we perform constant time operations, O(1), to check for consecutive numbers and update the maximum length. Since k is at most n, the iteration step simplifies to O(n). Combining these steps, the overall time complexity is O(n). Regarding space complexity, the frequency map stores at most n entries, requiring O(n) space. Auxiliary variables like max_length and number use constant space, O(1). Therefore, the total space complexity is O(n), dominated by the storage of the frequency map. In this section, let's discuss some common mistakes that can lead to incorrect or inefficient solutions for the longest harmonious subsequence problem. First, not sorting the array when necessary is a frequent oversight. Sorting is often crucial because it simplifies the process of identifying harmonious subsequences by ensuring that potential pairs are adjacent. Without sorting, you might miss valid pairs, as their elements could be scattered across the array. For example, with the input 4, 1, 3, 2, skipping the sorting step would mean overlooking the harmonious subsequence 3, 4. Another mistake is misinterpreting the problem definition. A harmonious subsequence requires the exact difference between the maximum and minimum values to be 1, but some mistakenly allow differences of less than or equal to 1, which leads to overcounting invalid subsequences. Additionally, using nested loops to brute force all possible subsequences can be highly inefficient, especially for larger inputs, as this results in a time complexity of O(n²) or worse. Lastly, overlooking edge cases, such as arrays with all identical elements, arrays of size 1, or arrays with no valid harmonious subsequences, can lead to runtime errors or incorrect results. These are critical aspects to watch out for when solving this problem. Another common pitfall is mismanaging frequency counts, especially when using a hash map. If you forget to check both number and number plus 1, you risk missing valid subsequences, particularly when the frequency of number plus 1 is 0. This is a subtle yet important detail to ensure your solution captures all harmonious pairs. Now, from an interview perspective, there are a few key insights to keep in mind. First, being able to recognize patterns is crucial. Many problems related to harmonious subsequences leverage frequency maps or sorting techniques, so pay close attention to constraints like the difference between maximum and minimum values. Using optimal data structures, such as hash maps, can also significantly improve efficiency by avoiding the overhead of sorting and enabling O(1) lookups. It's also essential to clarify the definition of a subsequence during interviews. Ask if it needs to be contiguous or if any subset of elements is valid. Interviewers often appreciate when candidates confirm problem details. Lastly, always consider time complexity. Aim for an O(n) solution whenever possible, as sorting-based approaches add an O(n) log n cost that may not be necessary. And remember to address edge cases proactively, asking about scenarios like empty arrays, arrays with no harmonious subsequences, or arrays with repeated elements. The concepts we've discussed so far are closely related to other problems on LeetCode, and tackling these can help you build the intuition needed for solving the longest harmonious subsequence problem. For example, LeetCode 1, the two-sum problem, also uses hash maps to efficiently find pairs with a specific difference or sum. LeetCode 128, the longest consecutive sequence problem, involves finding sequences with specific constraints, often using sorting or hash sets, which parallels some of the techniques here. Another useful problem is LeetCode 560, subarray sum equals k, which relies on prefix sums and hash maps to efficiently identify subarrays with a given property. These problems highlight the importance of recognizing patterns, leveraging optimal data structures, and efficiently managing constraints. Of course, LeetCode 594 itself, the longest harmonious subsequence problem, focuses specifically on finding subsequences where the maximum and minimum values differ by exactly 1, making it a natural extension of these related challenges. Solving these problems together can strengthen your grasp of efficient algorithms and problem-solving strategies. Let's now explore some alternative approaches to solving the longest harmonious subsequence problem and the trade-offs associated with each. One common method is the sorting-based approach. Sorting simplifies the task of finding harmonious subsequences, as it ensures adjacent elements can be easily checked. However, this approach comes with the trade-off of adding O(n) log n to the time complexity, making it more suitable for moderate-sized arrays where this overhead is acceptable. Another approach involves using a hash map to store frequency counts. This method is highly efficient, achieving O(n) time complexity, but it requires additional space to store the hash map. It's particularly well-suited for large inputs where minimizing runtime is critical. Lastly, there's the sliding window technique, which applies only if the problem explicitly requires contiguous subsequences. While this is less common in harmonious subsequence problems, it's worth considering when the constraints demand both contiguity and harmonious conditions. Each approach has its own strengths and limitations, so understanding the problem requirements is key to selecting the most effective method. Great job! We've covered the longest harmonious subsequence problem and explored an efficient solution. Remember the power of hash maps for frequency-based problems. Don't forget to like and subscribe for more content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!